All right, today's topic is multiple regression analysis. We'll discuss mainly linear, but as you will see, it's not exactly linear when the number of regressors, the number of factors, increases more than 3. All right, so I hope that most of you still remember the single linear regression model discussion, because it will help us a lot. As you can see on the first slide presented, the general multiple regression model is very similar to the simple one regressor, one factor regression model. But the number of regressors, the number of independent variables is bigger. In very similar way, we use Greek letters to denote the population model, and Latin letters for the estimated or sample multiple regression model. And one important part of the model, of the global model, is the error, the random error. And of course, the goal when developing regression models is to have as small as possible error. And again, the main idea here is that with the help of the breaking down the total sum of squares between the calculated and the real values, excuse me, we try to explain as much as possible from the dependent variable variation. And that means we can use the model, again, like the simple regression model, in two ways: to interpret the relationship between the variable of interest and a given regressor, given independent variable, and also to use the whole regression model to make predictions. The interpretation of the calculated coefficients is very similar. The intercept has also only mathematical explanation, interpretation, and could have business interpretation only if the value 0 is part of the independent, the regressor's data range, which could happen most of the time and only in finance. Because in finance, 0, as you know, means even negative values could appear. In other areas of the real life business, 0 and negative values are impossible. What is more interesting is about the slope. In general, again, we say that it estimates the average value of the change in the dependent variable when the regressor, the independent variable, increases by 1 unit. That's exactly like the single regression equation. The average change in dependent variable for 1 unit change in the regressor. But now, because we have many other regressors, this relation is not anymore simple. I'll return to this explanation. Just let me clarify what do I mean. Let's use now, let's say, 2 variables regression model. Now the line, the regression line, as a matter of fact, is not a line anymore. It's a plane. Can you see? It's a plane with 2 slopes. What's happened if we add 3 variables? It becomes kind of a cube, maybe, or 3D surface. And if we have 4, then it's impossible to explain it. That's why when we interpret the meaning of any given slope, because there are many, not only one. Here, as we can see, there are many in general. Let's use the number k. Then the interpretation of any slope becomes slightly longer and a little bit more complicated. In the beginning, we say again that it shows on average the change independent variable y for one unit change in the given regressor, given predictor, given independent variable. All these terms could be used. And now we continue, holding all other variable constant. Or we can also say net of all other changes, or net of all other variables changes. And because of this, it's referred to as a partial regression coefficient or net regression coefficient. But it's not a mistake to call it in general just a regression coefficient. Why we add this second part, holding all other variables constant or net of the changes in other regressors? Because we keep them, if we keep them constant, then in the multiple regression model, everything else is constant, and only these changes, and then we can say, and we can interpret only one regression coefficient. Otherwise, if we try to explain all of them when they change, all of them simultaneously, it's simply impossible, as we saw when increasing the number of variables. And also, let's return to the goal. The goal, technically, as I told you, is to estimate a regression equation which minimizes this error. And this error is the difference between real values and the estimated, the calculated values. Just to remind you, the sum of differences between real values and their arithmetic mean property we learned long time ago in chapter 2 is, or chapter 3 actually, chapter 3 is always 0, which logically means that no need of regression equation because the arithmetic mean value will minimize the sum of differences, this error, because it's always 0. But there is no also logic because using arithmetic mean to explain the relationships or to make predictions is not a good idea. Because of this, as we did in single regression model and equation, we will minimize the sum of squared errors. This area here, not just the linear distance, but the squared error. This has also another advantage. This advantage is that squared values for large errors are much bigger, because this is a square, than the linear errors, which is another hint when evaluating the model accuracy to test these squared differences, because somehow they penalize the large extreme errors. But we'll talk about this in a few minutes. Let's continue, and in a similar way as we did with the single regression equation, analyze the multiple regression error. What else? The assumptions are very similar. But now we have not only one, we have more than one predictor, regressor, that adds one extra step, the so-called model specification, that is to decide which variable to add. Why? Because not all provided are significant. And as a first step in this, we can use correlation matrix. Correlation matrix, which, as we know already, returns pair-wise correlation, meaning pair-by-pair correlations, linear coefficient of correlation between all variables. And we'll take only the first column that interprets or returns the coefficient of correlations between the dependent variable and the regressors. We'll discuss this tomorrow in more details in our lab. Then we use, here is an example, we want to analyze the sales change using two regressors, price, the cost of advertising. We start with coefficient of correlation. We analyze, both of them are moderate, not very strong. And the scatter diagrams also show some pattern, but not very strong. And in the past, probably a researcher wouldn't waste more time, but simply will go back and look for other, let's say, customer demand. Demand is always a good regressor when we want to explain and predict company sales. But nowadays, having Excel and PHStat and other statistical software, this will be returned in a second. And as we'll see, there is one extra step provided by PHStat, the stepwise regression, which automatically will select the best set of independent variables. Only when the number of the regressors is more than 8, it doesn't work well. That is, there is a limit, and probably in case of big data problem issue, when we have to analyze tens and maybe hundreds of dependent variables, we should look for better statistical software. And once we evaluated, we estimated and defined the possible number of significant variables, we just need to run regression, as we know already, in Excel or PHStat. Sometimes, like this case, we can do it immediately because there is not too many variables to identify. And once we get the regression output, as we know it already, it's very similar to the regression output from the single regression equation, but we have now one extra step. As you see, the significance of the whole model is not the same as the significance of any single coefficient. That's why we'll have two steps when analyzing the error. Otherwise, from the given output, we can continue first using the model and make the interpretations. Now, for example, the advertising slope could be interpreted as the average change in sales by when the cost of advertising increase per 1 unit, that is $100 per week. And we add net of the changes or net of the effect of changings due to price, or simply holding the price constant. Otherwise, we cannot make good interpretation. And then we can use it to make predictions. For example, if we want to find what are the expected sales for price of $5.5 and advertising cost of $350, we simply take the regression model from the output, substitute here, excuse me, substitute the unknown values for price and advertising, and solve the equation for sales. Of course, with the help of PHStat and other software, we can make this automatically because the program returns a special output for the confidence intervals, and here it's interactive, and as you'll see tomorrow, we can change these values here, and that means we'll find as many predictions as we want. Now, let's return to the so-called error. The error, as we know, can be used when constructing the confidence intervals, otherwise directly is useless. But the first step is using the sum of squares, that is the numerator, and breaking down or dividing the numerator in two parts, as we know from ANOVA, explain, unexplained, we can test and validate the significance of the whole regression model. Why? Because the explained part of the variation here is due to whole regression equation. That is the ANOVA table that we can find in the regression output, as we see here, can be used to test and validate the regression model significance by two statistics. First one is the coefficient of determination, as we know, the R squared, and second one is the analysis of variance or ANOVA table. But let's return again to the table, the output from Excel and PHstat. Here, as you can see, there are two R squares with different values, R square and adjusted R square. One step at a time. R square is simply the sum of squares due to regression divided by sum of squares total. That means it's a ratio. If R square is not presented, then very simply dividing regression sum of squares due to regression or explained sum of squares to the total sum of squares, and we can calculate exactly the R square value. How did we interpret it? Simply the percent of explained variance independent variable due to whole regression model. But why do we have two different R squared values? Let's move to the next step. What is adjusted R square? Adjusted R square is R square which takes into account the number of degrees of freedom. Let me remind you, in ANOVA table, we can see that there are different number of degrees of freedom. And the value of the explained variance depends on the degrees of freedom. The larger the number of predictors, and the larger the number or the larger the difference between the adjusted and non-adjusted R square. So which one to use when analyzing the explained variation? Always it's better, especially when we want to compare different models, we must use the adjusted R square, which, as we can see, is not even 52, it's 41.17%. Not too much explained variance. And by all means, as I mentioned in the beginning, comparing the coefficient of correlation, this is a signal that we must add more regressors. But suppose that there are no more regressors, and we can continue and test the whole model and then see what predictions and explanation it will return. So next step, as I mentioned, two steps to test the model significance. Step number one is using ANOVA table to test the whole model significance. Here the null, we use F-test, again, null hypothesis, similarly to when we use for the first time ANOVA, then was that all arithmetic means for all groups are 0, and alternative, no, at least one is not 0. In a similar way, we set up here null hypothesis, which says that there is no linear relationship. That is, all regression coefficients, all regression slopes are 0. Alternative hypothesis, no, at least one is not 0. And we test this hypothesis using F distribution and n minus k minus 1 or n minus, in parentheses, k plus 1 degrees of freedom. N is the sample size, k the number of regressors, and 1 is, as we know, the first degree of freedom which we use when calculating the standard deviation. And then we simply test F. calculated F value. No need when we use Excel, PHStat, and other statistical software like Minitab, Stat Graphics, and so forth and so forth. Why? Because in the ANOVA table they return, they provide immediately the p-value, not necessary to compare the calculated F value with the critical F value. It's better directly to use the p-value and make conclusion. Why directly the p-value? Because, to remind you, the p-value immediately shows the minimum level of significance at which we can reject the null hypothesis. And also whether this test, this decision is strong or not. So for 1.2%, we can say it's almost very strong, or at least it's a strong evidence to reject the null hypothesis, meaning that in this case, the calculated F value is somewhere in the region of rejection. And we make conclusion that given the sample data at 0.05 level of significance, we can reject the null hypothesis. This is the technical explanation, and then it means that the regression model does explain a significant portion of the variation in pi sales. And there is evidence that at least of the regressors affects the pi sales. Which one? We don't know. That's why we run the second step, the individual test. Here, using t-statistic, we test individual hypotheses for each slope, not for the intercept. As I told you, we do not interpret, do not test the intercept. So the first one is that the slope for the price, prices, sales prices, are not significant. Alternative, that they're different than zero, meaning they are significant. And second, that it's about the cost of advertising. And how do we test this? We test using the third table, the regression model table, which returns not only coefficients, but their standard error, their calculated t-statistic, and finally the p-value. We test, as I told you, each coefficient individually, and we make conclusions whether to reject the null hypothesis about insignificant slope or to reject, that is, to accept the alternative hypothesis, meaning that the slope is significant. And not only this, the table also returns the confidence intervals. The confidence intervals, as we know, are calculated adding the error. And immediately, if zero is part of these confidence intervals, it simply means that we cannot reject the null hypothesis. But as we can see, none of these intervals contain zero. That is, we can reject the null hypothesis for all coefficients, even in this case, including the intercept. Then, how to use the error further on? Okay, the error, as I told you, we can use when calculating the prediction intervals. I'll show you quickly today, and we'll do it in the example tomorrow. But now let's return and continue the statistical analysis of the regression model. All right, as I told you, we use it. First, the error to compute the prediction interval. And by the way, good professional in this area, in this business, directly from this prediction range can say whether the prediction is good or not. If the prediction interval is too big, too large, apparently the forecast is not very good, which means no matter that regardless the fact that we validated a significant model as a whole and significant regression coefficients, we must improve the model because the error and the prediction intervals are still too big. And finally, do not forget, as I told you, usually I recommend, and I always do this before I make predictions and interpretation of the results. I test the assumptions that is the aptness of the model, and the assumptions of the least squares technique, which, to remind you, mean to look for random pattern in the residual plot, that is no patterns of nonlinear correlation and relationship, no homoscedasticity, meaning the variance is constant, okay, and also that the residuals are independent from the regressor, each regressor. Otherwise, there will be a pattern. Fortunately, Excel, PHStat, they draw charts for all residuals, and the only chart which sometimes we need to draw and test is the box and whiskers plot, to analyze the normal assumption, normal distribution of the residuals, the errors in the model. And how do we test this? Okay, first we can use histogram, normal probability plot from Excel, or we can draw now both in Excel and PHStat the box and whiskers plot. And again, like here, but it's from different, this is the chart from a single regression equation. The house price is a function of the house size which we use, and here, as we can see, the chart, the residuals plot, looks pretty random. Now we have one interesting example, and I will talk a little bit more because in tomorrow's class we have also similar variables. Sometimes when we have special variables like male or female, or other qualitative variables that have no numerical explanation, we can code them, and then we present them as special kind of regressors or dummy variables. But once we use them, then not a problem. Here, like student in a college, yes or no, is used as 0 and 1 value, and we simply run regression equation using these dummy variables. And we test, and we analyze the residuals and so forth. But now, let's return to the multiple regression model. As I told you last time, there are two important issues in multiple regression model. And everything starts with the model building, when we use not the best subset or the best set of independent variables, regressors. What may cause this? If the number is too large and stepwise regression in Excel doesn't work, then we simply guess. And when we add, or we can use also correlation metrics, assuming that we will not use very strong related regressors. Why? Because this will return a very, I would say, not just boring, but it's really dangerous problem. The problem of multicollinearity. This is when the high correlation exists between two independent variables. This we can identify directly from the correlation matrix. In the correlation matrix, as I told you, we can see not only the correlation between the dependent variable and the independent variables, but also between the independent variables itself. For example, here cars and advertising and sales force, or in our case with pies and pie sales and price and advertising. Here apparently the coefficient of correlation between advertising and price is so small that it's insignificant. But also to remind you, the correlation between pie sales and price and advertising also are not very high. That's why by all means in this example we must look for more regressors, more significant variables. Let's return now to the problem of multicollinearity. What's happened when the problem exists? So when the problem exists, sometimes it's even impossible to apply the least square technique because it requires in mathematics reverse matrix, which must use some calculations which divide or use in the denominator value very close to 0. As we know from math, we cannot divide by 0. 0 is not acceptable for the denominator. And because of this, the results from the regression analysis, they become unstable and insignificant. How to identify and test the availability of multicollinearity? Sometimes even if we have a relatively strong relationship between two regressors, it doesn't mean that the multicollinearity problem exists. That's why we can use another test. This test, which PHStat and Excel provide, is the variance inflationary factor. When its value and it's calculated regressor by regressor. If this value is greater than 5, then this is not good, and we have to analyze further on the problem of multicollinearity between this regressor and the rest of the predictors. If all VIF values are less than 5, then no problems, no issues, and we can continue further on. But that's not everything. As I told you, this is the output from the PHStat about the case, the price, about the cost of advertising and pie sales. But this is only one of the real issues. The other issue, as I told you, it may, by the way, it may exist in both single and multiple regression models. And it depends on the nature of our data, especially and unfortunately in real life business, most of data we use are time series data, meaning data collected or samples drawn over time. And why this is dangerous? Because let's quickly analyze. There is other classes when we'll analyze in more details the autocorrelation and time series. But as we can see here, usually historical data or time series data are connected with each other. And if we calculate a special test, the Durbin-Watson statistic, we can test a hypothesis whether there is significant autocorrelation in the model, that is, in residuals, or not. Unfortunately, sometimes the Durbin-Watson statistic return inconclusive decision, but if this happens, we can use other statistic, which is simply first-order spurial correlation. That means this is the coefficient of correlation between historical data, the current data and the data from the previous period. And we can test it with standard coefficient T statistic. And if this model is this coefficient is significant, that means that there is autocorrelation in our residuals. And this is not good, and we must eliminate the autocorrelation. I'll just mention here quickly how can we do this, but also, as I mentioned, in other classes, the further CS 240 class, I believe very soon it will be, there are two classes now, FINE 460, Econ 460, very soon it will be Management 460, Business Forecasting and Predictive Analytics, when we will develop many more regression and other predictive models. And first one is adding new variables. As I told you when we were just a few minutes ago discussing the pie sales, and I told you probably adding customer demand will immediately increase the significance of the model and reduce the error in predictions. Like here, sales in the beginning, in this example, in other class, I'm just using data. First, when we calculate sales only as a function of the income, then Durbin-Watson return small value when the Durbin-Watson is less than 1 or bigger than 3. By all means, it's a significant correlation, autocorrelation. But when we just add the rate, inflation rate, I believe, immediately the Durbin-Watson, as you can see, jumped to 1.98. Wow, it's almost 2. And the value of the Durbin-Watson statistic is from 0 to 4. And between 1 and 3, or let's say between 1.5 and 2.5, by all means, there is a significant autocorrelation. And value very close to 2 means definitely just adding one new regressor, we eliminate the coefficient, the autocorrelation problem. What else can we do? Just to remind you, when we did 2 sample tests of hypotheses from dependent samples or from the same population, then we cannot use the standard technique. And what did we do? We use the differences between these 2 variables. Differences is very good idea, but in statistics, not only differences are in use. You can take the log of the logarithmic values of one of the variables. You can square the variables or take square root or reciprocal values. The problem is that they don't have good business interpretation. The only good business interpretation is when we use differences. Why good interpretation? Yes, because in time series, the difference between 2 consecutive values is simply their growth. The process growth. So sales in the current period minus sales from the previous period is simply the growth from this historical period. That's why differences, working with differences is very common practice in statistics. But we can also make some other transformations to eliminate the autocorrelation, like adding time as dependent variable, or using more advanced techniques like autoregression or autoregressive models. That is, using time lags or historical data for the same variable as regressors. That means, for example, sales is a function of sales from the previous period. Now, let's just for a second think logically. If we use, let's say, seasonal data with 4 seasons, what time lag we can expect to be significant? 4. Why? Well, because it means that spring sales, most of the time we can expect to be dependent from the spring sales in the last year. Not always, but usually. Or sometimes we don't know, and we must run a special test to identify the significant time lags. Could be how in general we identify the total number. It depends on the time series. If we use seasonal data, then the potential number of time lags is 4. If we use monthly data, then it will be 12. If we use weekly data, then it will be 5 in general, but sometimes for businesses that are 24/7, we can use 7. As I mentioned, this increased the complexity of the regression analysis, and fortunately, it's not part of our current class. That's why we'll stop our presentation here, and we'll continue with questions and answers about the quiz.